I once harbored dreams that in the next life, I might be born as the child of a billionaire, but there exists a hypothesis suggesting that there are only infinite repetitions of this very existence. Imagine yourself seated in a cozy room, with the gentle glow from a desk lamp casting its light upon an ancient book, and beyond the window, a soft breeze carrying the rustle of leaves, as if whispering the universe's secrets. That is the sensation one experiences when beginning to ponder time, not as a river flowing ceaselessly onward, but as a closed circle, where everything returns to its origin. We customarily believe that time advances solely forward, akin to unrelenting footsteps along life's path, bearing hopes for a fresh and distinct future. Yet mathematics, with its cold precision, reveals to us a harsher truth, one that stirs the heart, blending fear with awe. It is the universe quietly awaiting its reversal, like a river that ultimately bends to reunite with its source. This may sound akin to mysticism, reminiscent of fairy tales told by a grandmother beside the hearth, where souls wander through successive lives, but it is inscribed in mathematics, etched into formulae and theorems that scientists have devoted lifetimes to uncovering. It is an inescapable fate, namely the Poincaré Recurrence Theorem, named after the French mathematician Henri Poincaré, who lived at the end of the 19th century and the beginning of the 20th, a genius who discerned hidden laws amid chaos. This theorem asserts that, provided a system possesses finite energy and adheres to deterministic laws, all its states will one day return to the initial configuration. Envision it thus: the universe as an immense sphere, with particles of matter dancing within, and no matter how they collide or whirl, they will eventually rearrange themselves precisely as they began, like a melody that repeats upon its conclusion. Regardless of the complexity of its trajectory, no matter the depth of chaos, as long as it remains within a bounded space, it cannot evade its cyclic destiny. This implies that the universe does not progress linearly but cycles, like the steady heartbeat of a colossal being, where each pulse marks a cycle of birth and demise. Chaos is not an eternal escalation, but a repetition, much like storms sweeping across the ocean only to dissipate and yield to calm, merely to return with comparable fury. Time is not an arrow, hurtling straight ahead without retreat, but a boomerang, flung afar only to arc back to the thrower's hand. Consider the moment you inhabit now, with the laughter of friends echoing in the air, the warm aroma of coffee diffusing, and a sense of hope filling your chest. All of this will recur, not as a hazy dream, but as sharp reality, repeating eternally. At this juncture, one might inquire, how can the universe be finite? How could infinite space repeat? Scientists of yore also presumed the universe might be infinitely vast, but reality often proves cruel, much like realizing that youthful dreams do not always materialize, and one must confront life's harsh boundaries. The observable universe's size, like a sphere of light within which we perceive, boasts a diameter of approximately 93 billion light-years, teeming with galaxies, stars, and planets. The uniformity of the cosmic microwave background radiation, the echo of the Big Bang, pervades space evenly like a subtle symphony, attesting to the universe's large-scale homogeneity. The density of dark energy is finite, a mysterious repulsive force accelerating the universe's expansion, yet not boundless. The discrete structure of quantum states, where energy divides into minuscule, discontinuous packets, all evidence converges on the same conclusion. The universe is not infinite. It is merely so vast that it appears so, like an ocean so expansive that sailors lose their way, though shores exist somewhere distant. And provided space is finite and time infinite, repetition is not a probability, but an inevitability. According to the latest research, as of 2025, from the James Webb Space Telescope, we have uncovered ancient galaxies at the observable universe's edge, hinting that the universe may approach a finite end, perhaps a big crunch in roughly 33 billion years if the cosmological constant proves negative, as proposed by certain physicists at Cornell University, and supported by recent dark energy observatory data indicating a potential reversal of expansion. These discoveries deepen the Poincaré Recurrence Theorem, for if the universe is finite, cyclic returns become unavoidable, rendering us minuscule before such grandeur, yet inspired as participants in a grand cosmic dance. Furthermore, observations from the telescope have revealed unexpectedly mature galaxies forming mere hundreds of millions of years post-Big Bang, suggesting accelerated processes in the early universe that align with models of bounded, recurring systems. As inquiries into quantum mechanics grow profounder, this conclusion evokes increasing despair, like gazing into existence's dark abyss, where all seems meaningless due to repetition. In the quantum realm, a peculiar rule governs, where particles are not tiny spheres, but probability waves spreading outward. A particle's state evolves not in physical reality, but within a mathematical space termed the Hilbert space, named after the mathematician David Hilbert, an abstract realm where vectors represent states, and operations preserve probabilities. Provided this space is finite, quantum states cannot advance indefinitely. They will one day revert to prior positions. This is not mere possibility, but certainty, as demonstrated in recent experiments at the Vienna University of Technology, where researchers have proven Poincaré recurrence in multiparticle quantum systems, envisioning electrons dancing and returning to original spots like an endless waltz. Building on this, a 2025 R14 paper titled A Blueprint for Experiments Exploring the Poincaré Quantum Recurrence Theorem outlines protocols for observing such recurrences in controlled quantum environments, providing fresh insights into how thermalization emerges in isolated systems and reinforcing the theorem's applicability to quantum chaos. We perceive ourselves advancing forward, believing the future unfolds step by step, each decision infused with freedom's breath and hope. Yet the mathematical model's responses border on cruelty, like a biting chill piercing the skin. Time is not a straight line, but a sealed loop. The path you tread is duplicated infinitely, like old films projected repeatedly in a dim cinema, where you are the audience, reliving familiar emotions. And the progress you sense is merely another return point, a transient halt in the circular journey. At this point, the astute might invoke the law of increasing entropy to counter. For we know entropy can only rise, rendering the universe ever more disordered, like a cluttered room left untidied, with objects scattered everywhere. Thus, it cannot revert to the past, nor repeat. But many overlook a crucial premise. The second law of thermodynamics is not an absolute natural edict, like an unyielding stone wall. It is merely a statistical law, describing how most scenarios unfold, based on probabilities amid billions of random particle collisions. Yet this does not imply it holds eternally, for in probability's domain, rare exceptions and unexpected fluctuations always lurk. And the Poincaré recurrence theorem's retort is colder and more merciless, inducing a shiver before mathematics might. Provided the probability is not zero, however minuscule, like a grain of sand in a vast desert, it will assuredly occur, given sufficient time, perhaps 10 to the power of 10 to the power of 26 years or more, per chaos theory calculations. The universe will manifest an unimaginably tiny fluctuation, like a gentle ripple on a serene lake, yet sufficient to alter everything. Such a fluctuation can transmute chaos back to order, reverting disorder to its origin, causing entropy to plummet rather than ascend, contrary to daily trends, but wholly feasible per statistical laws, as elucidated in Stephen Wolfram's explorations of the computational foundations of the second law, where he posits that the law emerges from underlying computational irreducibility in multicomputational systems, generalizing beyond mere thermodynamics to any rule-based evolution, with recent discussions in 2025 emphasizing its implications for quantum computing and emergent randomness. In that instant, the universe offers no explanation. It merely falls silent, allowing stillness to re-establish, like dawn after a storm, where all becomes fresh and pristine. For matter to reconvene, protons and electrons binding into atoms, then molecules. For galaxies to reform, with immense swirling gas clouds birthing stars. For life to re-emerge, from simple cells in ancient oceans to complex beings like ourselves. For civilizations to arise anew, with the first campfires, wheels, then computers and spacecraft. And you will reappear, with your first smile, youthful sorrows, and simple joys. And not once, but infinitely, until time loses meaning, dissolving into endless loops. If the universe possesses any form of memory, what it retains is not past traces, like faded photographs in a family album, but the unconditional repetition of each experience, akin to Roger Penrose's conformal cyclic cosmology, where each eon concludes in an infinite flat space, transitioning seamlessly to a new Big Bang, with cycles spanning about 10 to the power of 110 years, and remnants from prior eons potentially visible in the cosmic microwave background. A 2025 R14 paper co-authored by Penrose and Christoph Meissner, The Physics of Conformal Cyclic Cosmology, refines this model, addressing gravitational entropy and quantum implications, while recent analyses of cosmic anomalies bolster evidence for such cyclic transitions. Nietzsche termed this fate eternal recurrence, a concept he pondered deeply in works like Thus Spoke Zarathustra, linking philosophy to science, inspired by contemporaneous thermodynamics, now bolstered by the Poincaré Theorem. Philosophy endows it with meaning, a reminder of present life's value. Meanwhile, mathematics grants it probability, with the latest 2025 R14 papers on quantum versions of the theorem opening avenues for real-world experiments in quantum systems. Here, an unavoidable question grows perilous, like a sharp blade grazing the skin, compelling self-confrontation. If life is not singular, but reenacted across infinite time, with each joy and sorrow recurring. If you will once more return to this precise moment, with your heart pounding swiftly, breath warm, and thoughts streaming through your mind. If every action, all choices, every hesitation and omission will transpire infinitely in the future, then the question sharpens simply, like a whisper in the dead of night. Is the version of life you lead now worthy of eternal duplication? The answer belongs not to others, nor to the future, but to you alone, with your most authentic emotions. And whether you acknowledge it or not, you must bear responsibility for it. For if the Poincaré Recurrence Theorem holds, and with evidence from modern quantum mechanics and cosmology, it appears increasingly robust, then you do not merely have one life, you are compelled to live this present form infinitely until time ceases significance. So what is the question now? Do you wish for infinite future versions of yourself to persist in this current existence? If not, now is the sole gateway to change, like a door ajar in darkness, bearing hope's light. For in the next cosmic cycle, you might encounter this very narrative again, or read these lines, with an oddly familiar sensation. That would mean you have not yet altered, and by then, the opportunity for choice may have vanished. But now remains time to transform, unlike any future, for you still possess a modicum of freedom in this moment, with breath surging and heart beating fiercely.